All right. Hello, everyone. What we're going to be doing today is we're going to be talking about what's called implicit differentiation. So far we've learned a bunch of derivative rules, and at this point we could differentiate pretty much any type of function that we would have learned about in high school. So for example, I can make something look really complicated like y equals, say, x squared e to the x cubed sine of x plus ln of 2x plus 1 over arctan of x. And in theory, we could take the derivative of this function. I mean, it would definitely take a little bit. We'd have to use the quotient rule, the chain rule, the product rule, rules for sines and arc and inverse trig functions, rules for logs and exponentials. So we'd have to pull out all the stops for this one, but we could differentiate this if we needed to. So we could differentiate almost any kind of crazy function we can write down using things we learned from high school. But what I want to talk about today is a different type of differentiation that may also come in handy. So one thing to notice about this is that y is isolated on its own, or we could say f of x as well. The function, or y, or the dependent variable, is on its own. But as we've seen before, maybe in algebra or trigonometry, there are occasions where the x's and the y's may be mixed together on one side of an equation. And probably the most common example of this is in the equation for a circle. So let's take the equation for the unit circle, which is x squared plus y squared equals 1. And notice that we don't have y equals something, we have x and y mixed together on the same side of an equation. Now you might be like, okay, well, I could use algebra to solve this for y. So what I could do is I could subtract x squared from both sides to get this, and then I could take a square root. But the problem is with the square root, we end up getting this ambiguity where it could either be the positive square root of this or the negative square root of this. And what this means geometrically, if we were to draw the unit circle, is that the plus would correspond to the upper half circle here, and then the minus would correspond to the lower half circle here. So if we do want to solve this for y, we end up having to pick one half circle or the other. We can't have the entire equation of a circle if we just have y equals something. So the best way to express the equation for a circle is to have it written like this. And this is a situation like this where y is mixed into the equation with x. Y is implicitly a function of x. So even though we can't write it, this is called explicitly, where we have y on one side and all the x's on the other. It's going to be called implicitly if it's kind of mixed in right here. Now, this is a case where we could, in theory, solve for y, although we would have a limitation here. But there are going to be instances in the future, like, for example, let's say y cubed is sine of xy, for example. In this case, we can't solve for y at all. There's no way to just isolate y equals something and then only have x's on the other side. There's no way to do it for this. So this is y implicitly is a function of x, and you can't even write it in an explicit way. So let's say we want to do calculus with something like a circle. So a circle isn't a function. It needs to be defined implicitly like this. So if it's not a function, then what does it mean to take the derivative of y? Well, we can still find dy dx. That's still going to be possible. We can find the rate of change of y with respect to x, or the derivative of y with respect to x, but it's going to work a little bit differently than the way it may have worked before. So what I'm going to do is I'm going to take the derivative with respect to x of both sides of this circle. Let's say I wanted to find a derivative involving a circle. So let's see. So let's go through the motions here. The derivative of x squared, well, that just has x's in it, so we just do that normally. The derivative of x squared, as we've seen many times, is 2x. But then we get to y. Now remember, we're saying that y is implicitly a function of x. So y depends on x in some way. So what we're going to do here is we actually have a chain rule situation. If we have y squared, our outer function is the squaring function, and then our inner function is this y right here. So since we technically have one function, y, plugged into another, x squared, we need to use the chain rule to do the derivative of this. So the derivative of something squared, as we just saw, is 2 times whatever you're squaring. We have 2y, but then we multiply by the derivative of the inside here. Now the derivative of the inside we can call dy dx, because that's the derivative of y. So when we do the derivative of something involving a y, we do the derivative normally, so we get 2y out of this, just like you might expect. But then whenever we do a derivative involving y, we need to stick a dy dx at the end because of the chain rule, because y is itself a function of x. All right, so now we've handled that. And then the derivative of 1, the constant function, is 0. Okay, now unlike finding a derivative of, say, something like this, where once we go through the derivative rules, we have an answer, here we have dy dx mixed in with the x's and y's, just like we have a y mixed in with the x's and constants and other things here. So if we want to find dy dx, we need to algebraically solve for dy dx. So I'm going to subtract 2x from both sides. All right, and then I suppose I could divide by 2, which will cancel these 2's, and I could also divide by y. So this gives me that dy dx is negative x over y. Now, this is going to be our final answer here. So dy dx is negative x over y. Now, the cost of doing implicit differentiation, the derivative of an equation where y is mixed in with x, is that we may end up getting y's as part of our answer here. So we may have to have y mixed into the equation. But usually in the context where we have x and y mixed together, this isn't that bad of an outcome. So anyways, this is our dy dx for this situation. And note that dy dx for implicit differentiation means exactly the same thing that it does for explicit differentiation, or what we did in all the previous lessons. It still means the instantaneous rate of change of y with respect to x, and it also means the slope of the tangent line at a particular point. So this still means the slope of the tangent line. Okay, so now that we know our derivative formula for a circle, let's see if we can find where all of the horizontal tangent lines are and where all of the vertical tangent lines are. So the horizontal tangent lines, those occur when dy dx equals 0. Because when a line has a slope of 0, it's a horizontal line. So that means that negative x over y is equal to 0. So that implies that we're looking for where x is equal to 0. Now, it's not just any value with x equal to 0. We need to make sure that this value is on the unit circle somewhere. So we could either look at our graph here and see, oh, x equals 0 here and here, or we could do this algebraically and substitute it into our original formula. So we would have 0 squared plus y squared is 1, meaning that y squared's got to be 1, meaning that y could be either positive or negative 1. So combined with x being 0 and y being this, and by the way, we need to make sure y is also 0, because that would be an issue here. This means that we end up getting 2 different points where we have horizontal tangent line, one at 0, 1, and then one at 0, negative 1. And based on our knowledge of the unit circle, this makes sense. The coordinate for this point is 0, 1, and a flat tangent line. And the coordinate for this is 0, negative 1. And we also have a flat tangent line. All right. So that's how we get horizontal tangent lines. We said whatever derivative we have equal to 0. And note that sometimes this can result in more complicated equations where we have y's and x's mixed together. So you may have to deal with that, but this is how we find those horizontal tangent lines. Now we can also find vertical tangent lines. So vertical tangent lines occur as the derivative tends to infinity, or another way you can imagine this is that your denominator goes to 0. So we're looking for all of the instances where y is going to equal 0. And we also need to make sure that the top is not equal to 0. If they're both equal to 0, we need to simplify this in some way in order to see whether it's a horizontal or vertical tangent line. So if the top is not equal to 0 and y is equal to 0, or a denominator, then we substitute this into our original, see what x values we're going to get. We have x squared plus 0 squared is 1, and so this gives us a similar scenario to previously. X has got to be plus or minus 1. So this gives us the 2 points 1, 0, and negative 1, 0. And again, from our knowledge of the unit circle, we can see that these are going to be vertical tangent lines here. So this answer makes sense. So whenever you're doing a new concept, it actually pays to do it on something else that's familiar to you. Oops, I think I left that stuff down there, sorry. It pays to apply a new concept to something that you're familiar with so you can check your answer. Like we already know where the vertical and horizontal tangent lines of a circle are. They're on each of these kind of edges right here, where we have one coordinate being 0, the other being positive or negative 1. But we could get practice using implicit differentiation and then check our work here. All right, so let's go into some less conventional examples here. Something other than a circle. So now we can't use the picture to guide us. So let's find dy dx. And also you could write this as y prime. In problems where there are a lot of y's showing up everywhere, it may actually be better to do this because writing dy dx is a lot more strokes than just writing y prime. So find dy dx or y prime if tangent of xy is equal to ln of x plus ln of y right here. All right, so we're going to do the derivative with respect to x. Okay, so let's go to the left-hand side here first. So we see that we have x times y plugged into a tangent. So this means we're going to need to use the chain rule here because we have one function plugged into another. So the derivative of tangent, as we've learned previously, is secant squared. So we put in the original inside. Now notice we haven't differentiated a y yet, so we don't need the y prime here. But when we do the derivative of x times y, we will need to put a y prime near that. Let's do the derivative of x times y. Now we have two things multiplied together. So this means we're going to need to do a product rule. So I'm going to do the derivative of x first, and the derivative of x is just 1. And then I have a y right there, which I left alone. And I don't put a dy dx here because I didn't do a derivative of y or anything involving y. Next, I leave the x alone. The derivative of y will be dy dx. And in this problem, I'm going to call it y prime. I'll put that right here. And there we go. We did the derivative of these things multiplied together on the inside here. So we're done doing the derivative of the left. Right, next, we go over here. We have natural log of x. The derivative of ln of x is 1 over x. There's no extra y primes or anything because there are no y's right here. Next, we have the derivative of ln of y. And as we saw in the logarithmic differentiation section, the derivative of ln of y will be y prime divided by y. Or you could think of it as the derivative of ln of something is 1 over that something, and then we multiply by the derivative of what's inside. Okay, now our goal is to find y prime, right? But unfortunately, y prime is mixed up in the multiple places in this equation. So it's going to be a bit more difficult to solve than that situation. What I'm going to do first is I'm going to distribute this secant squared. So I have y secant squared of xy plus x secant squared of xy, y prime. I have the same left-hand side. What I'm then going to do is I'm going to move everything with y prime to one side of the equation. So I'm going to subtract this over here, and I'm going to subtract 1 over x over here. So I have y secant squared of xy minus 1 over x is y prime over y minus x secant squared of xy, y prime. Okay, now the reason for doing this, for getting all of the non-y prime terms over here and for all of the including y prime terms right here, is that I want to be able to factor y prime out of all of this. So when I do so, when I factor y prime out of this right-hand side, I have 1 over y minus x secant squared of xy. All right, so I want you to ignore the middle part of the equation here. We have y prime times this is equal to this. So all we need to do to get y prime on its own is to divide by this term right here. So if I divide this by this term here, I have y secant squared of xy minus 1 over x divided by 1 over y minus x secant squared of xy is y prime. So there we go. We solved for y prime. And in this situation, we definitely have a lot of x's and y's mixed together. Now, one thing we could do to make this look a little bit nicer, if you don't like these compound fractions, is I can multiply the top and bottom by x times y. So I can multiply the top and bottom by x to get rid of this, and I can multiply the top and bottom by y to get rid of this. So if I choose to do that, and you don't really have to do that, but it will look a little nicer if you do, then we're going to end up with, let's see here. We're going to have y squared, or xy squared, secant squared of xy minus y, all divided by x minus yx squared secant squared of x. All right, so there we go. So now we don't have any compound fractions here, but it's going to be a little bit messy no matter what. So there we go. So that's a pretty conventional problem where we have to solve for y prime given an equation where y is defined as a function of x only implicitly. And this is another one where we're not going to be able to solve this for y equals something with x because logs and tangents aren't very compatible algebraically. So we're not going to be able to simplify this very much. All right, so there's one example. Let's do a few more. All right, let's suppose, oops, there we go. All right, let's suppose in our next example that we have e to the xy squared plus y plus x equals 2. It's very common for implicit equations like this to have all of your variables on one side and then maybe a constant or 0 on one side. So this form is pretty common. All right, so I want to do the derivative with respect to x of this. And I want to find y prime. Okay, so first I'm going to do the derivative of e to the something. Now the derivative of e to the something, well, the derivative of e to something is e to the something, but then we need to multiply by the derivative of our inside. So we're using a chain rule here. And because these guys are multiplied here, we're going to have to use the product rule to deal with this. So I'm going to do the derivative of x first, is 1, and I'll leave the y squared alone. Since my derivative operation didn't touch a y squared here because we left that alone, I don't need a dy dx here. Then I leave my x alone. The derivative of y squared will be 2y. So I have 2, x I left alone, and the y. And then because I did the derivative of something with a y, by the chain rule, I'm going to get a y prime off of that. So this is my derivative of e to the xy squared, using the chain and product rules. I do the derivative of y, which is y prime. I do the derivative of x, which is 1. And then I do the derivative of 2, which is 0. Okay, now I'm going to use the exact same strategy that I used for the previous problem. I'm going to get all of my y primes on one side and all of my non-y prime terms to the other side. So if I were to FOIL this out, one of the terms would not have a y prime and the other would. So I'm going to, let's see, what am I going to do here? I guess I'll subtract all of the y primes over here. So I'm going to have y squared e to the xy squared, so that's this times this. And then I'm going to keep this 1 over here because that doesn't have a y prime. Now I'm going to subtract this y prime over to the side with 0, and I'm also going to subtract what I would have gotten here if I distributed. So minus 2xy e to the xy squared y prime. Okay, now just like before, our whole goal in doing this is to have a y prime in every term so we can factor. So this will factor into being negative 1 plus 2xy e to the xy squared y prime. And I pulled the negative out of both of these. And then finally, I divide this, my original left-hand side, by my factored right-hand side. So I end up with negative y squared e to the xy squared plus 1 divided by 1 plus 2xy e to the xy squared. And that will be y prime here. And you'll notice that a lot of times when we solve for y prime, there's going to be like a symmetry here. So you may see the same terms on the top and bottom, just with a different order or something like that. That's a pretty common way to see your answer for these problems. All right, so there's another example of implicit differentiation. Okay. Now, so far we've been doing implicit differentiation directly, where we just take the equation we're given and we just take the derivative immediately. And that seemed to work out pretty well. I mean, there's a fair amount of algebra, but that's going to be there no matter what. But sometimes we could do some algebra ahead of time to make our life easier. So in our next example, I want to find y prime again, only this time I have this sort of equation. The square root of x squared plus y squared is 3xy. Looking at this, and I think you can maybe solve this for y, though you may get into the plus minus situation we saw in the circle earlier. But what I want to do instead is, before I do any derivative, I want to square both sides of this equation right here. So if I square the square root, I get what's inside. And then if I square this, I have 9x squared y squared here. Okay, now with that done, I'm going to then do the derivative of this equation instead. And it's still an equation that's true and that involves y and x, so we can still figure out what y prime is from this new equation. So I'm going to do the derivative of this now. And the reason why I did that is that if we do the derivative of square root, we're going to have to use the chain rule, and then we're going to get things on the denominator, and it'll be a bit messier. But with this way, we only have polynomials or multinomials here to deal with. Okay, so I'm going to do the derivative with respect to x of x squared. That will give me 2x. I'm going to do the derivative of y squared. That'll give me 2y, but then it was a derivative with y, so y prime. Then I'm going to do the derivative of 9x squared y squared, and that will again involve a product rule. So I'm going to do the derivative of x squared, which is 2x. So combined with a 9, that gives me 18x. And then I leave my y squared alone. Next, I do the derivative of y squared, leave the x squared alone. And that gives me 18x squared y. And then because I did a derivative with y, we have y prime. Okay. Now, what I'm going to do is I'm going to do the same thing we've done for all of the problems here. And this is a very common strategy for these. I'm going to move all the y primes to one side, all of the non-y primes to the other, and I'm going to factor. Also, I could divide everything by 2, so I'm going to do that as well. So I'm going to have x minus 9x xy squared. So I divide by 2, then I subtract this over. And then I'm going to have 9x squared y prime minus 2y. Oops, the 2 went away. It's y prime here. So I subtracted this over, and then I divided by 2. Okay, and then as with the past two problems, I'm going to factor. So I have 9x squared y minus y times y prime, and then I'm going to divide. So I have x minus 9xy squared divided by 9x squared y minus y. And again, you can kind of see the symmetry here. A lot of times the top will be very similar to the bottom, only a negative sign may be switched around, or you have the roles of x and y reversed. So oftentimes there's going to be some symmetry in your answer. There we go. We were able to get y prime. Now, we probably could have also gotten y prime by differentiating the original equation. That would have been too bad, but I think it would have been more difficult than what we did. Okay, I want to go over two more things. One is something that we actually already know the answer to, but it's going to be a different perspective on that problem. So I want to find dy dx if y is arctangent of x. Now, we've already seen how to do this in a previous video, how to do the derivatives of inverse trig functions. And I mentioned then, and I'm going to mention now, arctangent is usually the most common one of these. So that's why I'm bringing it up again. So we already know what the derivative of this is. So we already know that y prime is 1 over 1 plus x squared. But what we could do is we can use implicit differentiation to see this in another way. What I'm going to do is I'm going to take tangent of both sides. I'm going to apply the tangent function to both sides. So tangent of y is, well, tangent of y. And then we have tangent of arctangent of x. But since these are inverse functions for one another, tangent and arctangent, you can imagine those as canceling out, and we end up just getting x. So this equation is really tangent of y equals x. Now, if we wanted to know the derivative of this, we want to know dy dx, we could take the derivative of both sides here. So the derivative of tangent we know to be secant squared. We keep the y in there. But then since we did a derivative with y in it, we have to multiply the whole thing by y prime. And then over here, the derivative of x is 1. So it turns out that y prime is 1 over secant squared of y. Now, with this one, we have y defined explicitly in terms of x, because we have y on one side, all the x's on the other. So we should be able to get an answer that has only x's in it. And if we wanted an answer like that, we would have to put back in the arctangent here. And then we have secant squared of arctangent of x right here. Now, how do we evaluate what this is? Remember, this is where we would end up drawing a circle, or sorry, a triangle. So we know that tangent of y is x. We can imagine this as x divided by 1. So if we have an angle y right here, we have x is our opposite side and 1 is our adjacent side. And if we use the Pythagorean theorem on this right triangle, we get that our hypotenuse is root 1 plus x squared. All right, so now let's go back to this. So we have 1 over secant squared of this, but 1 over secant is cosine. So this is really just cosine squared of arctangent. And cosine is going to be adjacent over hypotenuse. So this is 1 over root 1 plus x squared, but then it's squared, giving us the answer that we expected, which is 1 over 1 plus x squared. So this is sort of another perspective on derivatives of inverse functions. You apply the function to both sides, and you get that function of y is x. You do the derivative here, and then you do some algebra to get your y prime. So this is kind of another way of imagining inverse trig functions. Finally, I want to go over something that's pretty important for the future here. I want to talk about the mysterious number e. Now, we defined e in an interesting way earlier. I think we defined it as e was the number such that if we have e raised to the x, then it's going to be its own derivative. So we're going to say that was the definition of e earlier. But there's also another definition of e that we should pay attention to. So let's say in this example, we have f of x being natural log of x right here. So f prime of x, as we've seen earlier, is 1 over x. And in particular, f prime at 1 will be 1 over 1, or 1. Now, I want to write this in the limit definition because this is how we're going to get a better perspective on what e is. So remember, the limit definition of the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. Now, for our example here, f of x is ln of x, and x is equal to 1. So in our particular example, we have ln of 1 plus h minus ln of 1 divided by h. So this is equivalent to f prime of 1, which we determined by our derivative rule to be 1. Okay, so this is the main equation here. We have this limit equaling 1. Now, first of all, ln of 1 is 0. So we can get rid of this. We can just cross that off. Then we notice that we have the limit as h goes to 0 of 1 over h times ln of 1 plus h. And remember, this stuff is still equal to 1. Now, if we have a coefficient in the front, that could turn into an exponent here. So that's what I'm going to do here. And this kind of goes into my general advice that if we can use a log rule, it's probably a good idea to do so. So we have ln of 1 plus h to the 1 over h is 1. Now, what I'm going to do is I'm going to apply e to both sides here. So I'm going to apply e to both sides. And because the exponential function is continuous, I can do e to this limit and then just apply the e to the natural log here. And remember, e raised to the natural log, those will cancel out. So what ends up happening, we have the limit as h goes to 0 of the stuff we have inside. And then we have e raised to the first power, which is e. So it turns out that this limit here is equal to this mysterious number e. Now, this is an acceptable definition for e right here, but I think a more common one would be where we make the substitution h is equal to 1 over x. Then we have the limit. Now, if h is going to 0, that means that x needs to be going to infinity for this to work. So x is going to infinity, and then we have 1 plus, well, h is 1 over x, meaning that 1 over h is x. And since all I did was a substitution on the limit here, the result doesn't change. I just want to point out that this is also a very common definition for the number e. It's this specific limit. 1 plus 1 over x to the x equals e. And if you're interested, like, oh, well, why does this show up? Why would I care about a limit like this? This limit shows up when you're dealing with compound interest. As you compound interest more frequently, like weekly, daily, hourly, by the second, our equation ends up for how much money you would have tends to get something that looks like this in here, and then that will lead to e, where we compound something continuously. That's one kind of real world application that will eventually involve e in some way, though it also shows up, of course, in a lot of mathematics, mostly because of the fact, well, I don't want to say mostly because of the fact, but one way we're going to see this a lot is that e to the x is its own derivative. That's a very nice property of this number. But I just wanted to show you this limit right here because we're going to be using this limit in the future. In particular, we're going to be seeing this in calculus 2. All right, so that's it for today's lesson. So I will see you guys in the next lesson.